What's up guys, it's Imran Fiaz and today's video is on 2023 AQA level chemistry paper 1. Question 1, can't do transition metals, haven't gone through that yet. So skip all question 1. Question 2, can't do, haven't gone through standard electrode potentials in class. Question 3, obviously we can do this. Pair of 3 elements and their oxides. So, given the equation for the reaction between phosphorus and excess of oxygen, P4 plus 5O2 to form P4O10. Given the equation for reaction between sulfur dioxide, so firstly I'd write the formulas of these. It's H2O, and I'm going to form H2SO3. Give displayed from the anion form, negatively charged ion, when sulfur trioxide reacts with water. So S double bond O, double bond O. I'm going to have oxygen here. Oxygen here is an anion. Oxygens will be negatively charged. So something like that. Given the equation for reaction of magnesium with steam. So you form magnesium oxide plus hydrogen. It's very, I don't know how to say it, it's very unfortunate that, a lot of these questions in every A-level chemistry paper 1 are equation questions. Like, it's unfortunate because you have to memorize them, obviously, but then once you've learned them off by heart, it's very fortunate because of 3 marks. And I definitely need to go through all these equations again. So, an observation, white, solid. Given the equation, excess of magnesium oxide reacts with phosphoric acid. Magnesium oxide plus H3PO4. Is this equation in the CGP textbook? I'm going to check right now. And phosphoric acid and what is it with magnesium oxide? It's not. Yeah, it's not. Well, same thing would happen really. You just form. So you got 3 MgO here, 2 H3PO4, form Mg3PO4 2 plus 3H2O. 3 MgO plus 2 H3PO4 to form Mg3PO4 2 plus 3H2O. Nitrogen dioxide decomposes at a higher temperature. Note this much of salt nitrogen dioxide is placed in CO flask and heated until equilibrium is reached. Equilibrium flask contain this much oxygen. So, I'm just going to use the ice method. Nitrogen dioxide, nitrogen oxide, O2. Initially, nitrogen dioxide, I've got 0.317. And then at equilibrium, I've got 0.120 oxygen. So I've added 0.120. Therefore, I'm going to subtract, and for the nitrogen dioxide, we're going to assume it's also 0. So I'm going to add 0.120. It's a 2 to 1 mole ratio times by 2. So I'm going to get 0.240. Whereas with NO2, I'm adding here, I'm going to subtract 0.120 times by 2 because of 2 to 1 mole ratio. And that is 0.317 minus 0.120 times by 2, 0.0777, 0.077, 0.240 plus my answer, 0.317. Now to find out the mole fraction, I'm going to do 0.077 divided by the total number of equilibrium moles plus 0.240 plus 0.120. And I get for NO2 77/437 for NO. Just replace the numerator with 0.240, 240/437, and for O2 replace the numerator with 0.120, 120/437. But we do have to convert to decimals. That's 0.176. This is going to be 0.549. And this is going to be 0.275. 4.2 total pressure is that. Calculate partial pressure of NO2. So to find out the partial pressure of NO2, I'm just going to do the mole fraction of NO2, 0.176, times by the total pressure. That's why it's only one mark. 0.176 times by 120. 21.1 kilopascals. Question 4.3. It says table 1 shows mole fractions in different equilibrium mixture. For this equilibrium mixture, Kp is that. Give an expression for Kp. So Kp is obviously going to be Kp is curly brackets, pressure of NO squared times by the pressure of O2 divided by pressure of NO2 squared. Products of a reactants. And remember, including the moles. If it's 2 moles, it's squared. If it's 3 moles, it's cubed, etc., etc. And Kp is curly brackets. Use the expression and the data in table 1 to calculate the total pressure in the flask. Now, what I'm going to have to do is I'm going to have to set this whole thing equal to the total pressure. And in order for me to calculate total pressure, what I'm going to have to do is I'm going to have to say the total pressure, P, equals the mole fractions of all of these. So the mole fraction, I'm going to say lambda of NO squared times by lambda of O2 divided by any constant y and O2. Just let the examiner know, let lambda equal mole fraction divided by lambda of NO2 squared times by Kp. Let's substitute the values in. So 0.460 squared times by 0.230 divided by 0.310 squared times by 59.7, and I get 8.48 times by 10 to the power minus 3. So I clearly did something wrong. So if I look at it again, Kp is that, therefore it's going to be I did the expression wrong. P is not equal to that. Total pressure is equal to Kp times by NO2 squared divided by NO squared times by O2, and obviously it should be the mole fractions. So then if I do that, Kp 59.7 times by NO2 squared 0.310 squared, the mole fraction, divided by 0.460 squared times by 0.230, and I get 0.460 is squared. Yes, it is. 118 kilopascals, and that is correct. So, write expression out for Kp. Realize, okay, pressure, so I need to move everything to one hand side, so times by NO2 divided by this, and that will use more fractions, and I'll get the total pressure. Choose the effect of any other change in equilibrium, the value of Kp. Equilibrium mixtures compress in a small volume. Well, I know for Kp only temperature can affect the value of Kp. Of Kp. So compressing it into a small volume is going to have no effect on Kp. Effect on equilibrium yield of oxygen in a smaller volume, that's going to decrease then the equilibrium yield of oxygen. Yeah. Equilibrium mixtures are to reach equilibrium at low temperature, explaining why the equilibrium yield of oxygen decreases at lower temperature. Forward reaction is endothermic. So if I decrease temperature, it's going to shift to the exothermic direction to oppose the increased temperature. So what I'd say is, first thing I would say is that the forward reaction is endothermic. So if temperature is lowered, equilibrium shifts to the backwards direction, left hand side, exothermic direction, to oppose the decrease in temperature, hence increasing temperature. Reaction is endothermic. Equilibrium moves in backwards direction to left side to raise the temperature, to oppose the decrease in temperature, hence increase in temperature. Question 5. Question about metal chlorides. Table 2 shows some enthalpy change data. Use the data in table 2 to calculate the molar enthalpy change when calcium chloride dissolves in water. Calcium chloride, CaCl2. Yeah. When it dissolves in water, actually this is no. CaCl2 plus aqueous plus 2Cl minus aqueous, and I've got Ca2 plus gaseous and plus 2Cl minus gaseous. Calculate molar enthalpy change when calcium chloride dissolves in water. So from this to calcium chloride is minus 2,237, but I'm doing the opposite. I'm going from calcium chloride to this, so it's going to be minus 2,237. And then I've got Cl minus to Cl minus aqueous, minus 364 times by 2 plus minus 1650. The reason I times this by 2 is because I've got 2 chloride ions. Just to clarify, 2 moles of chlorine, Cl minus ions. And I want to find the molar enthalpy change when it dissolves in water. So all I'm going to do now, I'm going to do 2237, positive 2237, plus minus 364 plus minus 364 plus minus 1650 minus 141. Perfect. Kilojoules multiplied minus 1. Just remember to times by 2, and also remember this is to form calcium chloride. I'm going the opposite way to its reactant, so I'm going to do the negative on that. Negative of the negative, so become positive. Use the answer to question 5.1 to deduce how temperature changes while calcium chloride dissolves in water. What calcium chloride dissolves in water, the temperature changes. Well, because it's exothermic, because it's negative, temperature goes up. Well, I could say temperature increases. So a bit of a weird way of saying it, but yeah, temperature goes up, temperature increases because it's exothermic. If it's endothermic, I'd say temperature goes down, temperature decreases. Explain why the enthalpy of hydration of fluoride ions is more negative than the enthalpy of hydration of chloride ions. Fluoride ions are smaller, higher charge density, hence stronger attraction fluoride ion to electron deficient hydrogen in water. Question 5.4. Complete the Born-Haber cycle by writing the formulas of missing species on each of the two blank lines. Okay, so calcium solid plus Cl2 gaseous, and then this one's obviously going to be Ca gaseous plus Cl2 gaseous. That's the easy one. Then I've got this. Well, this is going to be then Ca2 plus gaseous plus 2E minus plus 2Cl gaseous. So Ca gaseous plus Cl2 gaseous, Ca2 plus gaseous plus 2E minus plus 2Cl gaseous. Pretty nice. Then it says, use figure 2 and data from table 3 to calculate second ionization energy of calcium, which is this. Well, what I would firstly do is, I'm going to let so this one's a bit more tricky. So I could say this, 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 and this is equal to this plus this minus this. Yeah, let's just do that. What is this? Well, that's the first ionization energy of calcium. It's got to be an easy way of doing it though. But let's just do it this way. I just want to get the marks. It is 2 marks. So minus 590 plus enthalpy of atomization of calcium minus 193 plus enthalpy of formation of calcium chloride minus 795 plus enthalpy of lattice formation of calcium chloride. It's minus 2237 pointing downwards, but I need to go upwards. So plus 2237. And that is going to be equal to Y plus enthalpy of atomization of chlorine 121, but I've got two chlorine, so it's going to be 121 times by 2 plus first is electron affinity of chlorine, which is also times by 2, so minus 364 times by 2. I have a feeling I could have made this a lot easier, but I don't know. So minus 590 plus minus 193 plus minus 795 plus 2237. Actually, let's just put that in a calculator and then plus 2237. 659. 659 equals Y plus 121 times by 2 plus minus 364 times by 2 minus 486. 659 plus 486. 1145. Let's go! That's obviously going to be positive. And the Mott scheme did it a different way. They just did formation is equal to the rest. which is actually probably a smarter way of doing it, but I preferred, I don't know why I did this way. Either way, you get the correct answer. Explain why the second ionization energy of calcium is greater than the first ionization energy of calcium. Electron is removed from a positive charge, positive ion. Okay, 6 marker. Okay. So stage 1, comparing the values for base. Stage 1, comparing values based on a perfect ionic model. Value for calcium chloride is larger, significantly larger, let's just say that, compared to potassium chloride and silver chloride. Well, why is that? Because the Ca2 plus has a larger charge, hence smaller ion, and whereas Ag plus and K plus have a smaller charge, hence bigger ion. Stage 2, comparing values based on a perfect ionic model to values, let's say, similarities. Perfect ionic between the perfect ionic model and the Born-Haber cycle values. So first things first, I can see that calcium chloride has similar values between perfect ionic model and Born-Haber cycle. KCl has similar values between the perfect ionic model and Born-Haber cycle values. What about silver chloride? Silver chloride has a very large difference, just 100 or plus. So I'd say calcium chloride and KCl are almost perfect ionic bonding. Ions are perfectly spherical. And in stage 3, the differences between the perfect ionic model and the Born-Haber cycle values, well, AgCl, silver chloride, has larger difference in values between the Born-Haber cycle and perfect ionic model. It should be the other way around, but it's fine. Why? Because AgCl contains some covalent character. Ag plus is more polarizing, hence distorts the electron cloud more. So, comparing the values based on perfect ionic model. Y is a significantly larger, large charge, smaller ion, whereas Ag plus and K plus have a smaller charge, hence larger ion, bigger ion. Similarities, well, calcium chloride are very similar. Perfect ionic model, Born-Haber cycle, same with KCl. Why though? Because calcium chloride and KCl have almost perfect ionic bonding, and therefore the ions are perfectly symmetrical. Say three differences. Well, silver chloride has a significant difference, larger difference than calcium chloride, potassium chloride, is because silver chloride contains some covalent character. Therefore, Ag plus is more polarizing, hence contains some covalent character. I think a lot of students will get that. Ag plus is more polarizing, hence distorts the electron cloud more. Question 6.1. Okay, question 6.1. Calculate mass of sodium barium hydroxide, of solid barium hydroxide, sorry, needed to prepare this much of that. So I'd find out the moles at 250 divided by 1000 times by 0.100, moles concentration volume. I want the mass. Moles is mass over mR. Mass is going to be the moles times by the mR. That's it. 4.28 grams. So 250 divided by 1000, basically times by and times by 0.100, and then times by 171.3, 4.28 grams. Describe the solutions used to make this a barium hydroxide solution and standard solutions and all of that. So transfer the solution to a volumetric / graduated flask. Add washing using distilled water and make up to the graduation mark, and then invert many times / shake to mix. Transfer solution to volumetric / graduated flask. Add washing using distilled water, make up to the graduation mark, aka 250 centimeters cubed. Invert many times / shake to mix. Suggest why is a good practice to rinse the pipette in this way. In the 25 centimeters cubed is rinsed with a small volume of the barium hydroxide, so that water does not dilute the solution. Suggest why is a good practice to remove the funnel from the burette before the titration. Drops of acid could fall into the burette, hence no longer know how much has been added from burette, decreasing tighter. Question 6.5. In different experiment, this much barium hydroxide, solid barium hydroxide is used to make this much of standard barium hydroxide. 25 centimeters cubed reacts exactly with this much of hydrochloric acid. Calculate concentration of hydrochloric acid. Okay, so what I do first is first thing I would do is find out the moles of barium hydroxide. That's pretty makes a lot of sense. Moles of barium hydroxide, and that's just going to be 0.952 mass divided by the mR, 171.3. times by 10, because you want it in 25 centimeters cubed. 5.56 times by 10 to the power minus 4. Or what I'd say instead is 0.952 divided by 171.3, and then divide your answer by 10 because that's in 250 centimeters cubed. I want 225 centimeters cubed. Then I need to find the number of moles of HCl because I want to calculate concentration of HCl. I need to find the moles of HCl in 24.50 centimeters cubed. Well, I've got the moles. The only thing I need to notice that is the 2-to-1 molar ratio. So it's going to be number of moles is going to be 5.56 by 10 to the power minus 4 times by 2, 0.0011 moles. Then I know moles of concentration, volume. Concentration is the moles divided by the volume. Or the volume of what exactly? The volume of the HCl, 24.50. So I do that, divided by that. And don't forget, because I want it in moles per dm minus cubed. So it's going to be 0.00111. And you should get 0.045. Perfect. Times by 10 to the power minus 3. Because we want it in moles per dm minus cubed, this is in centimeters cubed. So 0.045 moles per dm minus cubed. Find the moles of barium hydroxide, 2-to-1, 1-to-2 molar ratio, so times it by 2 to get the moles of HCl, and then rearrange to get a concentration. And how do you know this? Well, you know barium hydroxide is BaOH squared, hydrochloric acid HCl, and I know this barium hydroxide is used to make this much. This is to make this much of this, and it reacts with HCl. It's got to be balanced. If I've got, yeah, because if I do HCl, barium hydroxide, I get BaCl plus H2O. But if you look at that, it's not balanced, right? So then if I put a 2 here, a 2, because I've got 1, 2, 3, I've got a 2 here, and put a 2 here, and put a, no, that's not correct. Put a 2 there. You get the point. You could write the equation and deduce that it's 2-to-1 molar ratio. Equation between barium hydroxide solution and HCl in formula. Yeah, so it'd be BaOH squared plus 2HCl, BaCl, oh, BaCl2. I don't know how I didn't spot that, plus 2H2O. Yeah, okay, and then you get, this is used, identifies 2-to-1 molar ratio, and then you get that. Acid plus base, salt plus water. Classic. The uncertainty in this is that. Total uncertainty is that. Calculate total percentage error. So, I know the uncertainty in 25 centimeters cubed is 0.05. Then I know the uncertainty in the burette is 0.15. Nope, not 0.05, 0.15. And obviously I need to times this by 100. But what do I do to these? Do I times these or add them? Well, I want to find out the total percentage error. What I'm going to do is I'm going to add these two together and then 10 by 100, and you should get 0.81%. Question 7, can't do complexes and all of that. Can't do that. I could do 7.1, but yeah, it's just better to leave this whole thing. Yep, can't do this. Question 8, can't do. Yeah, I haven't gone through fuel cells in class. And question 9, yes, I have gone through time of flight mass spectrometry. Give me the equation for the formation of SR plus ions from SR by electron impact. So, for the formation of this from SR, so that's pretty easy then. Something like that. SR gaseous SR plus gaseous plus C minus. I know I'm forming this from this, so all you think I need to add is an electron, and obviously include the state symbols. That's maybe the hardest part, remembering to include state symbols. Then it says, so let's move this so I can read the question properly, because it's a 5-marker. It says a sample of strontium is analyzed by time of flight mass spectrometry. The sample is ionized using electron impact. The ions are accelerated to have a kinetic energy of 7.02 times by 10 to the power minus 20 joules. Alhamdulillah. An ion takes this long to travel along that flight tube. Deduce the mass number of this ion. So, what I'm going to have to do is, I've got the kinetic energy, I've got the length of the flight tube, I've got the time taken. I can find out the velocity. Yeah, I can find out the velocity, so let's do that. So the first thing I'm going to do, find out velocity. Well, I know velocity is distance divided by time. The length of the flight tube is 95 centimeters, but remember it needs to be in meters. So centimeters to meters, I'm going to divide by 100. So it's going to be 0.95 divided by the time taken, 9.47 times by 10 to the power minus 4. That gives me the velocity, but I want the mass. Now I can rearrange the equation. So 2ke mass is equal to 2ke divided by v squared. Yeah. I've got the kinetic energy. Yeah, 7.02 times by 10 to the power minus 20 joules. 02 times by 10 to the power minus 20 joules. The velocity squared 0.95 divided by 9.47 times by 10 to the power minus 4 squared. What will that give me though? Put it on a calculator. 2 times by 7.02 times by 10 to the power minus 20 divided by 0.95 divided by 9.47 times by 10 to the power minus 4 squared, and then I get the mass is equal to 1.396 times by 10 to the power minus 25. Is this in grams or kilograms? It's going to be in kilograms because because mass is always given in kilograms for this. No, it's in kilograms. It is in kilograms. But obviously the mass of the iron, I need it in grams. So I need to now times it by 1,000. So I get 1.39 times by 10 to the power minus 22 grams. I want to find out the mass number of this iron. So first thing I'm going to have to do is times by L, which is 6.022 times by 10 to the power 23. And that's what I have to do now. 1.39 times by 10 to the power minus 22 times by 6.022 times by 10 to the power 23. 83.7, so therefore 84 is the mass number. So find the velocity using distance divided by time. Very simple. Then rearrange the equation to get mass is equal to 2ke divided by v squared. I've got the kinetic energy. I've got velocity, I just worked out, squared. Then what is this giving me? Well, that's in kilograms. Remember, mass is always measured in kilograms in time of flight mass spectrometry. So therefore that's in kilograms, but I want to find the mass number of iron in obviously grams. So then I need to times by 1,000 to get it in grams, and then to find the mass number of this iron, I don't divide by Avogadro's constant, I just times by Avogadro's constant, and that will give me 83.7 something, 84. It gives me 83.7058, that would be 84 as a mass number. Explain how the ions are detected in a time of flight mass spectrometer. So, the idea that ions hit a detector slash negatively charged plate, and each ion gains an electron, generating a current. How relative abundance is determined? Relative abundance is determined as proportional to current. All I'd say is current is proportional to abundance. Okay, 2 more questions left for this. Says question 9.4, sample of strontium contains 3 isotopes. 82% is that. I want to find out the relative atomic mass. So usually with these type of questions, it gives me the relative atomic mass, but in this case, first it wants me to find out percentage abundance of 88. Oh, it's 2 parts. Okay, so I know. Okay, so I've got 88 SR. 82% is 88 SR plus 86 something plus 87 something. And I know it's a 1 to 2 ratio, so I can say 86 x 87 x. No, it's 2x. $86x. Okay, let me try this again. There's a reason this question is near to the end of the paper. It's not meant to be a particularly easy percentage abundance or relative atomic mass question. 86x plus 87 bracket 100 minus 82, which is 18. 18 oh, I just overcomplicate things a whole bunch. Didn't have to do any of that. I was thinking, why is it not asking me to find out? Why is it not giving me the relative atomic mass? Because this is a different type of question. Yes, a lot of the times you need to use algebra to do that, but in this type of question, it tells me it's in a 1 to 2 mole ratio, the percentage of abundances. So all I need to do is 100 minus 82, 18, and therefore it's split into a 1 to 2 ratio. The total is 3, 18 divided by 3, 6, but 87 is 2, so it's just going to be 12. It's just going to be 6 times by 2, which is 12%. Then to find the relative atomic of the sample, it's very easy now. AR is going to be 88 times by 82 plus 87 times by 12 plus 88 times by 6, no, plus 80, no, 88 is 82, 87 is 12, therefore 86 is 6, divided by 100. Obviously I should have worked it out, but in this case I'm not. So 87.8, it wants to 1 decimal place. So this bit's easy once you've done the first part. We just try. It's the way it's presented is slightly deceiving in my opinion. Yeah, other isotopes of that total must be 100. 100 minus 82 is 18. It's a 1 to 2 ratio. Add up the total ratio 3. 8 divided by 3 is 6. But because I want 87 one, which is 2, 6 times by 2 is 12. Electrospray ionization energy is used instead of electron impact for ionization energy of protein in mass spectrometry experiments. Suggest why. The protein does not break up. The protein does not fragment. Protein does not break up / fragment. Therefore, electrospray ionization energy is used instead of electron impact. Question 10 is a question about weak acids. Identify the indicator as most suitable for use in titration between propanoic acid and sodium hydroxide. Thymol blue. Bit of a weird question. Next part, nice one. Remember Ka, square brackets, CH3, CH2, COO minus H plus divided by CH3, CH2, COOH. Calculate the pH of this, give you answer 2 decimal places, and it's giving me Ka. So first thing I can, because I know this off by heart, which you should know, Ka equals 10 to the power minus pKa. Therefore, Ka is going to be 10 to the power minus 4.87. That's the first thing. Second thing is, yeah, all I've done is added propanoic acid, so it's going to be pure. So what I can say is Ka is equal to concentration H plus squared divided by HA. Because concentration H plus equals concentration A minus. So I don't need to say K is equal to concentration H plus A minus divided by HA because I can't use that. So therefore I need to then rearrange it. So I get concentration H plus equals square root of Ka, which is 10 to the power minus 4.87. Ka is 10 to the power minus pKa, times by HA 0.100. Then to find a pH, it's pH equals minus log 10 concentration H plus. So square root of 10 to the power minus 4.87 times by 0.100, and pH is minus log 10 of my answer, and I get 2.94. Perfect. 2.94. Question 10.4 and then 10.5. 10.4. It doesn't say buffer, it says butanoic acid. Ka is that. This much sodium hydroxide is added to that much of butanoic acid. Calculate pH of solution formed. Okay, so first thing I'm going to do, moles of sodium hydroxide using concentration times by volume. And I'm going to go through all these steps in this case, show the working as well, because it's why not, it's the second to last part of the question. And then the moles of butanoic acid, methane, even propane-butane. I'll just say HA because that's what it's going to be really. 25 divided by 1000 times by 0.100. Before I do that, then I'm going to construct the equation HA plus OH minus arrow A minus plus H2O. So 20 divided by 1000 times by 0.100, 2 times by 10 to the power minus 3. 25 divided by 1000 times by 0.100, 2.5 times by 10 to the power minus 3. So let's write that down. This is 2.5 times by 10 to the power minus 3, and this is 2 times by 10 to the power minus 3. Sodium hydroxide, the hydroxide ions. I'm going to minus from small number, minus 2 times by 10 to the power minus 3, that gives me 0, minus 2 times by 10 to the power minus 3, and therefore on the right hand side I'm going to add 2 times by 10 to the power minus 3, which is just going to be 2 times by 10 to the power minus 3, and then 2.5 times by 10 to the power minus 3 minus 2 times by 10 to the power minus 3, that'll give me 5 times by 10 to the power minus 4. Okay, now H2O, yes, the same would happen, 0 plus 2 times by 10 to the power minus 3, 2 times by 10 to the power minus 3, but I don't care about moles of H2O. Why? It's not in the K expression, not in the K expression. So I've got this. I now need to rearrange Ka. Well, Ka equals concentration H plus times concentration A minus by concentration HA. Therefore, concentration H plus equals Ka times by concentration HA divided by concentration A minus. And now, yes, I'm going to do it as well to find the concentrations, but in actual reality the concentrations would cancel out. The volumes would cancel out, so there really is little to 0 point finding out the volume of divided by the volumes. But yeah, to find the concentration of HA, concentration A minus, it's going to be the moles 5 times by 10 to the power minus 4 divided by the volume, because moles concentration, volume concentration, moles divided by volume, which is 20 plus 25, which is 45 times by 10 to the power minus 3, and for A minus it's going to be 2 times by 10 to the power minus 3 and divided by 45 times by 10 to the power minus 3. But in actuality the volumes would cancel out anyway. Now I put it into my calculator. Ka, it gives me in the question 1.51 times by 10 to the power minus 5, right here, butanoic acid, times by concentration HA, 5 times by 10 to the power minus 4, divided by 45 times by 10 to the power minus 3, or if you just left it as moles it'd be fine since the volumes would cancel out, divided by 2 times by 10 to the power minus 3, divided by 45 times by 10 to the power minus 3. That will give me the concentration H plus ions. Concentration H plus ions equals 3.775 times by 10 to the power minus 6. That's not my answer though. That's not what the question's asking me. The question's asking me for the pH. The pH, I don't know why I drew arrow from Ka to there. pH is minus log 10 concentration H plus. So therefore, I'm just going to substitute this into here. So it's going to be minus log 10 of my answer. I get pH as 5.42. And you should always give it to 2 decimal places, but it doesn't ask us in this question anyway. 5.42. Find the moles of butanoic acid, find the moles of sodium hydroxide, find the moles of acid, 5.0 times by 10 to the power minus 4. And you've also got and you've also got the 2 times by 10 to the power minus 3, and you should get that. Then it says 10.5, a student plans to titrate butanoic acid solution with a solution of ethylamine. Explain why the titration could not be done using an indicator. Well, ethylamine, this is a weak acid and weak base / alkali titration. Hence, pH change is too gradual at equivalence point. So color change of indicator is difficult to judge. And that is the end of the 8th grade A-Level Chemistry 2023, Paper 1.